All right, that's enough. Enough from you. Enough from you. This is my time. So exam 4 is next Monday. So what's that? The 21st? And the topics are going to be no, I can't because I haven't written it yet. So free body diagrams, Newton's second law, and circular motion. Really all of this stuff is just Newton's second law, Newton's third law, a couple different applications of it. And it's cumulative, so all the stuff before. I'm going to do one more circular motion example problem. Maybe I should do two. But we're not going to spend a ton more time on that. And then we're going to move on to the next stuff that isn't on the test. So if anybody has any questions about stuff related to the test, I'd be happy to answer those. Does anyone have any homework questions? Or maybe I should actually, let me answer questions about the test I just handed back first, and then we'll go into that. So, yeah, anybody have any questions about exam 3? I know like a lot of people were feeling bad about the helicopter question, but really people mainly did pretty well. Are there any you'd like me to go over? Yes?
Yeah, would you do 4A?
4A, yes. 1. And then does anyone have a question about 2 or 3? Maybe I'll just do them in order. 1, so exam 3. The coordinate system was like this. So there's the x-axis, there's the y-axis. And the vectors, there was one that made a 40-degree angle and had a magnitude of 10. And then there was another one that had a magnitude of 8.5. And so in this coordinate system, the angle that we need for this vector with a magnitude of 10 is just positive 40 degrees. It's just 40 degrees counterclockwise from the x-axis to the vector. So this is just 10 times the cosine of 40, 10 times the sine of 40, and that is 7.66, 6.43. And then the 8.5, that's 180 degrees. You could do 8.5 times cosine and sine of 180. Or you could just notice that this is in the negative x direction. And so you just get negative 8.50. And so if you add those two together, 7.66, 6.43 plus negative 8.50 is negative 0.84, 6.43. And then the way to do the graphical part of that is put these vectors head to tail, draw the vector that goes from the free tail to the free head, and then just think about what the components would be. So I'm going to do it like, so there's one like this, there's one like this. So the resultant vector looks like this. And if you put the tail of the resultant vector at the origin, that red resultant vector looks, plausibly like negative 0.84, 6.43. So it makes sense. Any questions about any of those? And then the second one, a ball is thrown into the air from a height of 2 meters at an angle of 25 degrees from vertical. So its path looks something like this, where this angle is 25 degrees. And that means that this angle is 65 degrees. So if I put a coordinate system on the ground underneath where it's thrown, what are we trying to figure out? How far does it travel horizontally before it hits the ground, and what's the velocity just before it hits the ground? So for both of those, we have to figure out how long it takes to hit the ground. So we want to find TF. We know PIX is 0. PIY is 2. We know the acceleration. The final position, we know that PFY is 0 because it hits the ground. The initial velocity is, its initial speed is 15 meters per second, so the initial velocity is 15 times cosine and sine of 65. Can someone tell me what those two are?
6.339 and 13.595.
Okay, and then we don't know anything about the final velocity. So to get the time, we'll say PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0 is equal to 2 plus 13.52 TF minus 4.905 TF squared. And you can use the quadratic formula. This is A, B, C. And what are the two roots you get there? Okay, so TF is, so negative 0.1491. We want the positive one. And so now to figure out how far it travels horizontally, we'll just use the x equation. So PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0, plus 6.34 times 2.91, which is 18 something. What's the decimal? 18.45 meters. And then for the second part, we're just trying to figure out the velocity right before it hits the ground. So just use VFX is equal to VIX plus AXTF. Plug this one in. And VFY is equal to VIY plus AYTF. Plug it into that one. And two things that you can use to sanity check the answer you get is we know that the x component of the velocity should stay the same. That never changes in a free fall problem because the acceleration of gravity is just vertical. So that needs to stay, what did I say, 6.34. And then the second one, the y component needs to be negative because it's on the way down towards the ground when it, right before it hits the ground. So if you get a positive answer, you know something went wrong. Any questions about that? And then 3, the velocity is this way. And so for part A, if the object's speeding up, the parallel part of the acceleration has to be in the same direction. If it's not turning, the perpendicular part has to be nothing. And so for part A, the possibilities are A is equal to 10, 5, the exact same vector, or 2, 1, or 20, 10. They just have to have the same ratio and be going in the same direction. And then if it's slowing down, it's the opposite thing. You have a velocity like this. You have to have a parallel part of the acceleration this way and no perpendicular part. So the acceleration is negative 10, 5. Negative 10, negative 5. Or negative 2, negative 1. Okay? Okay. So remember that multiplying a negative number times a vector, let's call the vector AB, gives you components negative A, negative B. And physically what it means to multiply a vector by a negative 1 is you switch the head and the tail. And that's exactly what you need to do to make for the acceleration to make something slow down. So negative 1 times a vector like this is the opposite. So those two things together are why you have to make both of the two components negative. Any other questions about that one? And then 4, helicopter is traveling with a velocity vector of 5.5, 2.5, so its velocity vector is like this. And it drops an object when it reaches a height of 20 meters. And the object will follow a path like that. It starts out with the same velocity as the helicopter, which means it'll go up a little bit higher, not very much, because the helicopter isn't going up very much, very fast. And then it'll start to fall down. It'll follow this parabolic path. And it asks, what's the displacement vector from the point of release to the highest point? So I'm going to put the coordinate system down here like I usually do. We don't know T final. I guess we might as well find that. We know the acceleration. We know the initial position. We don't know anything about the final position. We know the initial velocity is 5.5 for x and 2.5 for y. And we know that the final velocity, y component, is equal to 0 because that's how you specify the highest point. And so we use VFY is equal to VIY plus AYTF. So 0 is equal to 2.5 minus 9.81 TF. So TF is equal to, I think it's about 0.25 seconds. And then you can plug that into these two equations. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. And then PFY is equal to PIY plus VIY TF plus 1/2 AYTF squared. And once you have that, the displacement vector is PF vector minus PI vector. And then part B, it asks how far it travels horizontally before it hits the ground. So we need a new time final. So time final now is when it hits the ground. We want to find time final. We know the acceleration. We know the initial position. The final position, we know the y component is 0 because that's how you specify the ground. The velocity is the same, the initial velocity, it's what's given. 5.5 for the x component, 2.5 for the y component. And that's all we need. So PFY is equal to PIY plus VIYTF plus 1/2 AY TF squared. Solve that for TF. And then plug that into the x equation. Any questions about that? Okay. Anybody have any questions about homework before I go on to the stuff we're working on right now? Like friction problems, any of those sliding or rolling problems? Somebody, I thought, said... You know this class has like 48 people in it? Yes? Sure. I don't have it with me. That's okay. Oh. Yeah, that's sort of ignore that. Ignore number 2. That's a waste of time.
Which one?
On what's that, Newton's second law? Newton's second law, number 2.
Ignore A or B?
I think the whole thing.
Number 2?
Yeah. That's the benefit you get for coming to class tonight. Yeah, it's like the force, what's the force vector applied by the ground to that? I don't know. 11?
Yeah. No.
Which one is that?
That's one we don't have to worry about either, right?
Just, let me see.
That's the box on the box.
Oh, that one's really hard, yeah. There won't be anything like that on the test, but I think it's good practice, you know what I mean?
Yeah.
But there won't be anything that hard on the test.
Can we go over number 1, the circular motion?
Yeah. Okay. You have that one? All right, so number 1 says a 100 kilogram object moves counterclockwise in a circle of radius 20. So there's the circle. The radius is 20 meters. Counterclockwise, so it's going this way. Horizontal to ground. Its speed is constant at 5 meters per second. And there are 4 points listed. At the bottom is the point A. Then at the left is point B. The top is point C. And the right is point D. And for each one of those, we want to calculate the velocity and acceleration vectors. Okay, so at point A, the velocity vector is going to be tangent. I'm just going to draw them first because we're going to need to know these directions. So the velocity is like that. Is there any parallel part, any tangential acceleration? How do we know? That's right. How do we know that there's not? Because it's a constant speed. And then it's turning. What direction is the centripetal acceleration? It's centripetal. That's what that means, towards the center. And since that's the only part of the acceleration, that's the total acceleration too. So the velocity vector is the speed times the cosine and sine of whatever angle this is. I haven't chosen a coordinate system yet, but let's use this one. So the velocity is 5 times, well, that velocity vector is in the positive x direction. So it's just positive 5 in the x direction, 0 in the y direction. At A, yep. So it'll be, yeah, these will be different. The magnitudes of those vectors are going to be the same everywhere, but the directions are going to change at each one. And then the total acceleration is equal to the centripetal acceleration. And the centripetal is the speed squared divided by r, pointed in that direction. So that's 25 over 20. So that is 5/4, 1.25 meters per second squared in the positive y direction. And so in components, that's 0, 1.25. And since this is uniform circular motion, the total acceleration is equal to that centripetal. So that's at the point A. And now at the point B, the velocity, it's tangent to the circle, so it's this way. The centripetal acceleration is this way. So the velocity is in the negative y direction. It has a magnitude of 5, so it's just 0, -5 meters per second. And the acceleration is equal to the centripetal acceleration, which is 1.25, because the calculations of the magnitude are all the same. So 1.25 meters per second squared in the positive x direction. So that's 1.250. Okay. And so one thing that's easy to do here is it's easy to think, you want a vector from the center to the point that you're looking at, and then you get the component backwards of your centripetal acceleration. Remember that the centripetal acceleration goes from the point that we're thinking of toward the center of the circle. So that arrow always goes towards the middle. And then C, the point C, the velocity is this way. The centripetal acceleration's this way. So the velocity is in the negative x direction. So the velocity is negative 5, 0. And the acceleration is in the negative y direction. So that's 1.25 meters per second squared that way, or 0, negative 1.25. And then the last one at D, the velocity is this way. The centripetal acceleration is this way. Okay, so the velocity is in the positive y direction. So 0, 5. And the acceleration is in the negative x direction. So that's 1.25 this way, which is another way of saying negative 1.25, 0. Any questions about that one? E? Oh. What is the net force vector applied to the object in part A through D? Okay, so it's 100 kilograms. Wow, that's big. Newton's second law says F net is equal to the mass of the object times its acceleration. So for the point A, F net is 100 times the acceleration from A, 0, 1.25. So that's 0, 125 newtons. And then you just go around for each one and just plug in the new acceleration for the different points. One thing, part E here sort of shows mathematically, lets you work out why the net force is always in the same direction as the acceleration vector. If you multiply this number times a vector and you get something that's the size changes, but the direction has to stay the same. So like for the point A, the acceleration was in the positive y direction, and so the net force also had to be in the positive y direction, even though the magnitudes are different. Any other questions about circular motion problems? Oh, okay, that's right. I forgot about that. Can someone remind me what it was? So you already had time to work on it, and I was just going to do it today. Is that right? Yeah. Okay. Oh, yeah, right. So we did it once with one angle, and then we were going to do it again with a new angle. Um, so we did it first with like 45 degrees or something. And now we're doing it where this string makes an angle of 10 degrees with the horizontal. And so to go from this angle being 45 degrees to this angle being 10 degrees, it means you have to swing it a lot harder. It has to be going a lot faster to stay up that high. And we wanted to see, so the mass of this thing was 0.06 kilograms. The horizontal distance, which is the radius of the circle, was 0.25 meters. And we wanted to know what's the tension in the cable and the speed. Do anybody have it like accessible what those values were for 45 degrees? Uh-huh. Or just for the cable tension and the speed? Okay, newtons. 1.55 meters per second. Okay, so when we do the new calculation, are we going to get bigger or smaller values for those? Bigger for both of those. It's going to have to go faster, and because it's going faster, that tension is going to be bigger. Okay, so for this kind of problem, for tetherball problems, we take a side view. So the view that's drawn here is the way we're going to do this problem. And the centripetal acceleration goes this way. And I'll use a coordinate system like this. The centripetal acceleration is v squared over r, pointing in the positive x direction. We don't know what v is, but we know r is 0.25, so that's v squared over 0.25 this way, which is 4v squared this way. And then in components, that's the positive x direction, so 4v squared and then 0 for y. The total acceleration is the centripetal plus the tangential. And this is uniform circular motion, so that's 0. How do we know this is uniform circular motion? Yeah, the tetherball problems, there's no way for that to be anything else if you're neglecting a resistance. And so now we'll go to free body diagram. There's a weight force of 0.06 times 9.81, so that's 0.5886. And then there's the cable force. So include a little stump of cable. The force goes right out of the stump, T. And this makes an angle of 10 degrees with the horizontal. So Newton's second law says 0, negative 0.5886 plus, this is T times cosine of 10 degrees, T times sine of 10 degrees, which is 0.985 T, 174 T. Is that right? And then those are equal to the mass times the acceleration, so 0.06 times the acceleration that we just figured out above, 4v squared, 0. And so we get two equations. The x equation says 0.985 t is equal to 0.24 v squared. We can't solve that because that has two variables in it. The y equation says negative 0.5886 plus 0.174 t is equal to 0. So this one we can solve for t. So what's 0.5886 divided by 0.174? Okay, 3.38 newtons. And is that tension bigger than it was before? That's what we expect. Yeah, the last one was 0.8. And now we can plug that into the x equation. So we get 0.985 times 3.38 is equal to 0.24 v squared. So v squared is 0.985 times 3.38 divided by 0.24. What do you get for that? Or just give me v, whichever one. For v. Okay, so v is equal to 3.37? 3.71? 3.71 meters per second. And is that bigger than the velocity before? Yep. So that all makes sense. Anybody have any feel for, okay, so as that angle gets smaller and smaller, what do you think, like, what do you think happens to the tension and the speed? Do they just keep going up towards infinity, or do they stop? Do they reach some limit, or do you have a feel for that?
Wouldn't the most angle go?
Yeah, right. That's exactly right. So the all we can do is approach an angle of 0. It won't ever start going above. It actually won't ever get to 0 either. But as you approach an angle of 0, as that thing gets closer and closer to horizontal, you get closer and closer to infinity with the speed and the tension. So if we did this at 1 degree, you'd have huge values. You know, if we did it at 0.1 degrees, bigger values. They just keep going up. And then does anyone have a feel for what the tension and speed would be as you approached an angle of 90 degrees. It's slowing down. So yeah, that speed is going towards 0. And you have a feel for what the tension is approaching? The weight, yep, exactly. So if you go down to 0 speed, the thing's just hanging there, and then the tension in the cable is just the weight of the ball. Yep. Right. Yes. Any other questions about that one? Yeah.
Just out of curiosity, why doesn't it ever reach 0 for an angle?
Because I can tell you exactly why. So I can tell you this without making anything up. Yeah, that's what I usually have to do. So if you got it perfectly horizontal, the tension's like that. The weight is this. Newton's second law would say T0 plus 0 negative 0.5886 is equal to the mass times 4v squared for the x component, 0 for the y component. And that gives you an x component, an x equation that's reasonable. It says t is equal to 0.06 times 4v squared. That's the same thing we had before, no problem there. But then the y equation tells you something impossible. Negative 0.5886 is equal to 0. And that can't be. Any other questions? Yep.
Could you walk through again how you got 4v squared?
Yeah. It was the exact same way that I did it in this example. Nothing changed since we don't know what v is. So, okay, let's go back to this picture. This is a tetherball problem, so we took this side view. Normally we take, in anything but tetherball, we take a view where we can see the circular path. But here we take this view, and then from then on it's all basically the same approach. We draw a vector that goes from the ball towards the center of the circle. The center of the circle is like right where I have the origin. And the magnitude of that centripetal acceleration is the speed squared over r. And so we get a magnitude, well, we get v squared over 0.25. 1 over 0.25 is 4. And so we get a magnitude of 4v squared pointed in the positive x direction. Any other questions? Okay, let me do at least one more example. So everything we've done so far is uniform circular motion. Now I'm going to do 1 or 2 examples where it's non-uniform. Nothing changes too much. You just have to, you follow the same steps, but then you just have to add in the tangential acceleration. So, non-uniform circular motion. Okay, so let's say that there's this kid sitting on one of those playground carousels that I don't think they seem to be, maybe you guys have never seen one. Matt's seen one before. They used to be all over the place, but I think they led to a lot of injuries and whatnot, which people used to think builded character. Okay, so you know these things I'm talking about? You probably read about them in your history books. And this thing's like rotating around this way. So let's say this kid has a mass of 15 kilograms. And the carousel has a radius of 2 meters. And at the instant shown, the kid's speed is 8 meters per second. And he's speeding up at, let's say, 20 meters per second squared. So first, what's the total acceleration? And second, what's the net force acting on the kid? And third, the kid's pant friction can hold up to a horizontal force of, let's say, 100 newtons. And so the question is, will he stay on? He should hold on to those handles. Then he wouldn't just be depending on the friction in his pants. Okay, so the steps are, it's not a tetherball problem. So the view that we want to take is one where we can see the circular path. And then we have to choose what point on this path we want to analyze. I don't know if there are any we haven't done yet. Let's do the one at the top. Really, any of these 4 points are kind of equally good. Anything that's not one of those 4 points is a bad idea, unnecessarily complicated. The centripetal acceleration is this way. He's going this way. So let's just figure out the centripetal acceleration, and then we'll come back and talk about the tangential. The magnitude of the centripetal acceleration is speed squared over r, which is, he's going pretty fast here. I don't think this is going to turn out well for him. So 8 squared over 2. So that's 32 meters per second squared. So just the centripetal acceleration alone, he's already doing a little over 3 Gs. And the direction is in the negative y direction. So that's 0, negative 32. And now we have to think about the tangential acceleration. So to do that, we'll draw the velocity vector, which is tangent to the circle, tangent to the path. And if he's speeding up, is the tangential acceleration in the same direction or opposite direction of the velocity? Same. So this is also the direction of the tangential acceleration. So the tangential acceleration is, what did I say the magnitude was? 15? 20? So the tangential acceleration is 20 meters per second squared, pointing this direction. That's the negative x direction. So that's negative 20, 0 for components. The total acceleration is the centripetal plus the tangential, which is negative 20, negative 32. And that's part A. So we wanted the kids' total acceleration. That's it. Any questions about that? If this kid weighs 15 kilograms, that's like 35 pounds, so he's like about 4. Just by the way. Okay, so part B. Now the total force. These numbers are not realistic, hopefully. Newton's second, yeah. We'll just, since we're just trying to calculate the net force, there's no benefit to drawing a free body diagram. The free body diagram is just how you figure out what all the individual forces are. So let's just go straight to Newton's second law, and we'll say F net is equal to the kid's mass, 15 kilograms, times the acceleration of negative 20, negative 32. And so that is negative 300 and negative 480 newtons. Both of these two force components are horizontal if you think about the orientation of this problem. And so the total, so for part C, I mean part B is really what we're going to be doing in this class in problems, but part C, that whole vector is horizontal. That whole F net vector. So the total horizontal force is the magnitude of that. So it's negative 300 squared plus negative 480 squared square root. Can someone calculate that for me? Anyways, it's a lot bigger than 100, that's for sure. He's long gone. He did not come close to making it to this point. Unless his pants ripped, and then he had a very high coefficient of friction between the steel and his bare butt. Okay, 566. So he's way off in the bushes.
So on the force net, the X is going off, but why wouldn't the Y go the same? Why wouldn't the Y go from the
Yeah, let's just draw this vector and sort of think it out.
why would
So-
why the force would be both of them being, but I suppose
Yeah.
it depends on where we are.
Okay, so yeah, let's think about what this force means and all that stuff. So we have a component in the negative x direction and a component in the negative y direction. So the force is like this. One of those, so I'll break it up into components. So this is F net. And what that net force does is it makes things change from, so things with no net force continue on the path they're on in a straight line with a constant speed. That's what happens if there's no net force. The velocity is constant. And so what this says is, in order for him to deviate in this way from moving with a constant speed in a straight line, he needs, so this one's 300, this one's 480. He needs a force of 300 newtons acting towards the center of the circle to make him turn, to keep him turning in that circular path. And he needs a force of 480 newtons tangent to the path in order to make him speed up that much.
Is there any correlation on that F net if that's the moment that he left the carousel, that's the direction he would go?
No. If the instant he leaves the carousel, and actually we're doing problems like that in lab tonight. So what happens if you're following a circular path and right at this instant, so you're following a path this way, right at this instant, the force that's making you follow this circular path disappears. That's what happens when all of a sudden you're sliding. Well, at that instant, your velocity is like this. So if all of the forces that are making your velocity change disappear, from that point on, you continue with that velocity. So this is the velocity that you would have from a top-down view. If you're looking from a side view, you know, the acceleration of gravity would make you, now you're in free fall. But horizontally, you'd have this. And the fact that you've been in this circular motion, this is sort of a confusing, surprising thing to people a lot of times at first. People tend to think that maybe the path looks something like this. You know, it still maintains some of that circular path or something, but that doesn't happen. What happens is once that force is gone that's making you accelerate, you continue in a straight line with a constant speed. And you see it, you know that Olympic sport, the hammer throw? Have you ever seen that? It's like the awesomest sport. The ones with the big guys in track. Oh, yeah, right. Yeah. Yeah. So they're like, they have a chain with a 16-pound ball on the end. That is heavy. So if you know shot put, like if you had friends in high school or anything that did shot put, it's a shot put on the end. And it, actually the high school shot put is 12 pounds, but this is 16 pounds. And this ball is, they're swinging this ball around themselves in a circular path. And once he gets this ball to about here, he lets go of it. And the ball all of a sudden is in free fall. And I forget how far they throw them, but like hundreds of feet. A 16-pound ball flying hundreds of feet. Be sure, if you ever watch a track meet, that you know that where the, you know, that you pick a seat somewhere where the hammer throw is not aiming towards. But from above, the path of the ball is a circle like this. They let go of the chain here, and all of a sudden it's just in free fall. And from that point on, in a top-down view, the ball is just following a straight path with a constant speed. Any other questions about track and field? All right, any other questions about circular motion? Okay, that's it.